Okay, so our next speaker is one who shares the name of with one of our very common people here in at SNEA. Tom Coughlan is, and there's Tom Coughlan. And our next speaker is Tom Coughlan. So I think I sent a urgent note to Marty one time. Your schedule is all wrong. Tom Coughlan has not joined Red Hat as far as I know. So so I was totally confused, but Marty set me straight. I think you're fixing the presentation. Are we all set? Okay, so I'd like to introduce Tom Coughlan from Red Hat, who's going to, the next speaker. We have 3 speakers in a row, really very focused on 3 operating systems. First, obviously, is VMware. Second is the Linux community with Red Hat, and then Microsoft. So, Tom, take it away.
Thank you. So I am relatively new to this group. I'm the engineering manager for storage in Red Hat Enterprise Linux. And I wanted to acknowledge Jeff Moyer. He's the fellow who's given this talk in the past few years, and he's done most of the work, and in fact did most of these slides. He's an engineer in my group. So, since the last time that Jeff was here, we've actually shipped support for persistent memory in Fedora, as well as in Red Hat Enterprise Linux 7.3. There's full support there for PMM as a block device, and then we have a technology preview for support with DAC. That's there as it stabilizes and matures, and as we start to gather user support. We don't currently have users, so we stop short of providing full support at this point, but that's coming, and you'll see that in the next few slides here. So since we've delivered this now, we've sort of put it out there, this talk is a bit more like a how-to do this on Linux in order to encourage people to start using it and to start developing and modifying applications. So it's sort of a basic block diagram of a kernel, a Linux kernel, and as you might imagine, when we add a new piece of hardware, we usually have to add a driver, and we might have to modify something in ACPI in order to detect it. In this case, it was a dramatic amount of work to support persistent memory. 2 file systems were modified dramatically. The VFS virtual file system with layers on top, the block layer, and the VM system as well, aging and so on. So this is just a view of the amount of impact this had on the kernel. Next is sort of the generic slide, similar to what Andy showed. Starting right here, this is the programming model for persistent memory. Starting right here in the middle, this is pretty much the standard block stack where you go through a standard file system. So you've got unmodified applications. We've talked about this before. One thing we haven't talked about too much is the BTT is the block translation table. This is used to ensure that we have sector atomicity, that under any circumstances that the sector will either be unmodified or modified, or you'll get an error when you read it, but you won't end up with a sector that's half-written. So that layer goes there, but the rest of this middle portion here is largely unchanged. Then we have the part we've seen over and over here with, in Linux, we have 2 DAX-enabled file systems and NVM library in order to allow application programmers to efficiently use the storage. This is as Andy described it. And then last, over on the left, is the tools and libraries and utilities that are there for managing the NVM hardware. And that's actually the next slide. So this shows you the primary command within Linux. NDCTL is used to manage your in this case NVDIMMs. So the system will boot up and you can type in this command and you'll see the devices that were discovered. In this case, as an example, there are 4 DIMMs. In the BIOS, before you boot the system, you can combine those into interleave sets. So in this case, we've combined 2 8-gig DIMMs into a 16-gig interleave set, and there are 2 of those. So here they are. And as you bring up the system, and NDCTL will display the namespace identifier, the mode that this namespace is in, and I'll get into that on the next slide, the size, and then where it says block dev, these are the device names that you'll see in /dev. So that's the main thing that the user might be interested in, is which one of these am I going to access when I go to use mount commands and make FS commands. So, as I mentioned, there are 3 modes, 3 namespace configurations that you'll encounter with NDCTL. The first is raw mode. This is the default, and you saw that in red on the last slide. This is a legacy mode. It supports DAX, but it does not support DMA. So basically, you don't want to use that. Instead, if you wanted DAX, you would use memory mode. Oops, sorry. You would use memory mode in order to get DAX with DMA. Next, sector mode. This is the block device that you can use as a traditional block device with atomic sector updates if you enable that BTT that I described, selectable sector size, and it includes diff-dix. This is the technique for end-to-end data integrity checking, where the application or the device driver can add a checksum, and that'll get sent out to the device, stored, and then read back on the read. And then finally, the third mode is memory mode. When we get to the point where we're going to start using this in Linux, every page of memory requires kernel page structure. And so that's mentioned here, and then the next couple of slides will get into some of the details on how you set that up on your system. So you need 64 bytes per page of page data structures. And in the case where your PMEM is relatively modest size, for example, 32 gig, then that comes out to be 512 megabytes. And you could, of page table entries. You could put those into your standard DRAM that you're using to run the operating system without any trouble. But in the future, when we get to terabyte and larger PMEM sizes, the page data structure table gets to be quite large, in this case 16 gigabytes. So if we provide an option to store that in the PMEM area instead of storing it in DRAM. So rather than use up your DRAM, you've got these terabytes of PMEM, you can put your page tables there. So the next couple of slides will show you how to do that. You have this, again, this option to select where those page tables are going to go. So you brought up the system and you type NDCTL and you see the device that we saw earlier. FDisk will allow you to see this device as well. Here you can see /dev/pmem0, and there's the size that matches what NDCTL sees. So the next step is to get this out of raw mode, because raw mode is not useful. And we're going to take the next step in terms of configuring this. We'll configure this as a memory device capable of DAX. And in this case, since it's a small device, it's a 16 gigabyte NVDIMM, we will use we'll put the page table map into DRAM. So this specifies I want the mode to be DAX capable memory device, and I want the page tables to go into DRAM. And then you see FDisk will show essentially the same thing with a slightly different size, because when you format the NVDIMM device, the raw device, there's some metadata that goes on there to track these changes that have been made, basically to record the configuration that this device is in. That gets written onto the device. It takes up 2 megabytes or so, or in fact exactly 2 megabytes of metadata space on the device. And that will show up there in NDCTL as well as XFS. Okay, so now, suppose you had a very large amount of persistent memory and you wanted to store the page tables in persistent memory because you've got plenty of it and it's less expensive than DRAM. Then you just specify math equals dev. The page structures, the page table entries will get stored right there in the persistent memory device, and so you can see the sizes shrunk a bit here because we're storing those page tables there on that device. Now, the next step I'm going to show is to convert this to a block device. Instead of using it as a memory device, we use it as a standard block device. And I thought I'd pause here and mention that when you do these NDCTL commands and change the mode, that's a destructive operation. The data that's on this device will be lost. So anytime you make a change, for example, moving the page tables from DRAM to PMEM would erase the data. Likewise, moving from memory mode to sector mode will lose the data. So there's something to be aware of there. So we're going to convert that memory device that we had earlier to a sector device. Simple enough, basically the same NDCTL style of command specifying the sector. It'll show you the default sector size 4K. And then it's PMEM0F for sector. So previously, if you're /dev/PMEM0 or 1, that indicates it's a DAX capable device. Here, the S indicates it's a sector device. This is a standard block device emulating a disk. And again, FDisk on that particular device will show the sector size at 4K, logical and physical sector size. So then the next step, of course, here is you can MKFS, XFS, or ext4, mount the device, and -O DAX, which is the field that specifies that you want to be able to do DAX on this device, and mount it. So there are just a few comments here, things to watch out for. If you take your DAX device and put partitions on there, standard Linux partitions, they have to be aligned on page boundaries. They are by default, so you don't have to worry about this. Just don't go and change that or you'll have a problem. XFS does require atomic sector bytes for its journal. Not true for the data, but for the journal that is required. And so what you would want to do is leave XFS in the default mode where it will use CRC for the journal data, and it will be able to detect errors if they do occur in the journal area on the DAX capable device that we're using in this case. And again, just a minor note, if the device is not capable of DAX and you ask for DAX, ext will fail the command. XFS will just log an error and continue on. Just things to watch out for. Okay, so as I mentioned, what we want to do here and now is start encouraging folks to start using this, modifying applications and so on. There is within the Linux kernel the capability of specifying a kernel parameter, a bouton, that specifies a portion of DRAM that you would like to emulate persistent memory. So there's the command. You'll reserve some space. You can set up multiple of these virtual devices within your memory. And when you boot, you'll see them as individual PMEM devices. They're not persistent because they're just backed by standard DRAM, but they will allow you to run these sorts of commands. And in fact, the performance is DRAM performance, which will mimic what you would get with an I'm sorry, NVDIM-N. And then the next sort of last bullet here is a little bit of an advertisement again. To get started on application development, use the NVML library. This is the library, suite of libraries that Andy described. That's where you want to get started. Lib, PMEM, lib, memobj. The second of these has the capability of transactional operations, and so that's probably the simplest way to start working with this. And then for more information, there's a pointer here to the PMEM.io blog, which was mentioned I think a few other times today. Future work that's coming in Linux in general and RHEL in particular. We need to follow up and make DAX fully supported on ext4 and XFS. There today it works, it's testable. We're again allowing some time for it to stabilize and to start develop actual users for that. We currently do not have support for installing and booting to PMEM devices. That is a fair amount of work, potentially affecting ACPI, UEFI, executive conduct, of course. There's work there that's not currently planned for 7.4, which is currently in development. And we'd be interested in hearing, and in fact, receiving code contributions already, that kind of work. Huge pages are there, of course, supported in the operating system in general. In the upstream kernel, there's support for huge pages with DAX and PMEM. This is not yet in RHEL 7. We're taking a look at that. A fair amount of work to backport that from the upstream kernel to the RHEL 7 kernel. Something we're looking at. Upstream Linux is working on 1 gig huge pages. That will require a substantial amount of work, potentially involving changes to file systems. That's not likely for RHEL 7, perhaps RHEL 8. But that's an upstream project that's being looked at. We're taking a look at being able to pass dev PMEM devices to the guest on a virtual machine within Linux. That's currently not there, but it's fairly close. It's something we're taking a look at, following up from the previous talk. So more refined error handling. We've heard a lot of talk today about error handling is hard. Today, for example, if there's a failure, the kernel will not allow the file system to be mounted. There's work being done there to allow the kernel to pass a signal to the user space indicating there's a problem, and then user space to deal with it more, obviously in a more fine-grained method than what we currently have, which is to take the file system offline. So there's work to be done to refine that. Upstream Linux, there are, and in fact in RHEL, there is this IO map infrastructure that's been developed. It helps to substantially improve performance in some cases. We need to do some work to extend that to the DAX version of ext4. And then there's always more performance work to be done. So in summary, persistent memory products are here today. NVDIMMs, and the capacities will substantially increase with 3D cost point. Linux has the capabilities I've described here, and that pretty much finishes what I have to say. There's some references here. You can take a look. Some of these have been mentioned in other talks. And that concludes the summary for what's going on in Linux.
Any questions for Tom? Okay, you asked a question earlier. I'm going to make you wait.
Same question. any redundancy consideration has already planned or implemented?
Is any redundancy consideration has already implemented or planned?
Redundancy. So of course, if you use it as a block device, then you can use software RAID and so on. I'm sure you're aware of that. In terms of redundancy for DACs, there's not work that I know of. Andy may know.
In the library.
It is there?
Yeah.
Okay, go ahead.
Outside the kernel.
What was that?
Outside the kernel.
Yeah, okay, outside the kernel in the user space libraries that Andy has described in his talk, there is some capability for specifying redundancy, data redundancy. Thanks.
Great talk, thank you. Same question I asked before. How much of this is x86 specific? Are you guys looking at enabling this on ARM, probably the most classic example for RHEL, and any other ISAs?
Fundamentally, I don't know of architecture-specific work that's been done here at a fundamental level. There's effort that's required around testing and so on. So we'll be selective. I think we'll pick architectures where there's a good business case, and then we'll have to do a substantial amount of testing. But I'm not aware of any fundamental architecture-specific options.
Any other questions for Tom? Okay, Tom, thank you very, very much.